many thanks to the organizers for inviting me to talk here and for the organization. So, well, the plan of this talk is basically my title here. So this is a work done with Damien Calaque and Scherotzke. So I'm basically going to give a motivation and application of what Sarah told us about on Tuesday. So starting with relative critical Loci, which is some kind of classical symplectic construction, which is very well studied with quiver moduli using the relative Calabi Yau structures Sarah told you about, and basically defined by Brav and Dykerhoff. And taking moduli of objects, we get these Calabi Yau structures become actually Lagrangian structures. And I'm going to try to give you a lot of examples of new Lagrangian subvarieties we can get in this context. And hopefully this will be of interest for people in geometric representation theory, as we know that Lagrangian subvarieties are of great importance in this area. So let me start with this symplectic motivation. So when trying to build and study new Lagrangian subvarieties, it might be useful to work with conormal varieties or stacks here. So I'm going to work with derived art in stacks. So you can consider a morphism F, and then make the following composition of Lagrangian correspondences. So the first one being just given by the zero section here of the stack in its cotangent, and the other one being here attached to my morphism F. So the composition just means that we take the pullback here, and that's how I want to understand the conormal stack. And well, the idea is to kind of deform this construction and define what we call relative critical locus of a function, or constrained critical locus. So basically you want to think of F as a constraint. And you see that the difference in this new diagram is that we replace the zero section by the graph of the differential of our function phi. Another way of seeing it as this diagram as a deformation is a deformation of the usual critical locus, which is obtained when the y is just a point. Okay, so that's what gives this name of relative critical locus. That can be, well, originally in the traditional symplectic literature is really related to problem of Lagrangian multipliers. All right, so I'm gonna give right away some example connected to quiver representations. So I can consider for F linear submersion, which is just a restriction of some representations of the three loops quiver to one fixed loop of this quiver, along with a potential that you've already heard of maybe on Tuesday in Tudor's talk, typically associated to this three loops quiver. It is given by x times the commutator of y and z. So in this, it actually yields a function of the representation of the three loops quiver, just taking the trace of a representation along this potential. And one can perform the few computations to actually get a precise description of this relative critical locus in this situation. So we no longer just have a triple of commuting matrices as we would get with the standard critical locus, but instead we add a matrix in the cotangent direction to small Jordan quiver in the 3 loops quiver, that actually is going to be equal to one of the commutators. Okay, so when we take a look at the image, so yeah, so I have to recall that these commutators comes from the partial derivatives of our potential with respect to each of the loops. And while the image we get in the cotangent of the representations of the Jordan quiver, which just means that we forget about y and z, well, it can be written this way. So we have a pair of matrices, x, and x star is going to be written as the commutators of 2 matrices commuting with x. Said in a more Lie theoretic way, you can think of x star here as something in the derived Lie algebra of the centralizer of x. So it turns out that we indeed get a Lagrangian subvariety. And by this, I mean that all of the irreducible components are Lagrangian. Okay, so the isotropic comes from the very definition of a derived critical, of a relative critical locus. And we can study by hand the irreducible components of this variety, and well, see that they are indeed half-dimensional. And I want to stress that even though we find that the irreducible components are again parameterized by partitions of n, it is actually different subvarieties than the standard conormal to the nilpotent cone. So that seems pretty new to us. I haven't seen something like that in the literature, but rather connected to Lie, maybe Lie theoretic problems through centralizers and stuff like that. All right, so another example. This time I'm so inspired by the Yang-Mills algebras in a very simple context, which is that this time embed a 1 loop quiver in a 2 loops quiver, and I consider this potential of degree 4. Okay, so you get these nested commutators here, and this time we get a relative critical locus given by a triple of matrices. Again, we have that the partial derivative of W with respect to X is going to be equal to some matrix in the cotangent direction, whereas the other partial derivative is going to be 0. Okay, so again, if you push this to the cotangent of Y, the space here, you get a Lagrangian subvariety described as a pair of matrices this way. Again, it seems to be pretty new. We haven't performed a thorough study of these irreducible components, but from the results I'm gonna give later, it is indeed something Lagrangian. All right, so far I haven't discussed about any group action on these quivers, on the multiple loops quiver, or with using the usual action of GLN by conjugation. And it is actually an interesting question to consider quotient stacks and understand their cotangent. So in the derived setting, the algebraic, non-commutative algebraic structure underlying such cotangent will be given by, to be vague, Ginzburg algebras. So considering an arbitrary quiver Q, what Sarah told us on Tuesday is, and that I rephrase here in this much simpler context, which is enough for me today, is that the cotangent to the moduli of perfect modules over path algebra of Q is actually can be described as the perfect modules over some dg-algebra denoted by G2 here, which is a non-deformed Ginzburg dg-algebra that can be defined this way, but which has a very explicit description. It's generated in degree -1 by some variable t that can be seen as an extra, a bunch of extra loops at each vertex. And in degree 0 by the doubled quiver, okay, with the differential, this map which yields a moment map when you consider the representations. So this is really the derived version of the preprojective algebra that can be retrieved when you consider just the zeroth cohomology group of this dg-algebra. And the fact is that it is a 2 Calabi Yau algebra, and that induces symplectic structure on its the perf of this algebra, and it actually matches the standard symplectic structure on the cotangent stack. Okay, so we can go further and try to understand critical locus, and we can consider as before a potential and a quiver. And again, let me recall you the construction that Sarah mentioned, I believe, on Tuesday, which is that we can build the deformation of this Ginzburg algebra, performing such a push out here. Okay, this has been later generalized by Keller, and this gives a 3 Calabi Yau DG algebra that, well, by definition, its perf will give the critical locus of the trace of the potential. Okay, because the critical locus, by definition, is actually the pullback of the perf of these guys. Which is the intersection of the graph of dw with zero section. Once again, this DG algebra defined by Ginzburg can be described very explicitly with these time generators up to degree -2 and a new differential between degree -1 and 0, well, given by the partial derivatives of our potential. Okay, but we want to go further. We want to study some relative critical locus. So we need something more, and that was one motivation to introduce again what Sarah mentioned in details on Tuesday, which is the fact that we can associate to any morphism of, say, DG category, but again here I'm just sticking to quivers, so R will be another quiver. In my example, it's just going to be a sub-quiver of Q, and G will just be an inclusion. So we can associate a 2 Calabi Yau structure on a cospan from the Ginzburg algebras associated to R and Q to what we call the G2 of this morphism G. So I recall the definition here. It won't matter in this talk, but the fact is that the induced Lagrangian structure that you get taking the perfect modules over these DG algebras matches the usual standard one on such Lagrangian correspondence. Okay, F here is just the pullback of G, so which is what I call the real restrictions to a smaller quiver. Okay, so now I have everything I need to understand the underlying DG structures of my initial diagram defining my relative critical locus. And to be precise, I can compose these two cospans here. So that I've got one cospan which is just a Calabi Yau map here, given by my potential, and I have another cospan that I just described above. Composition here as is just going to be the push out, which defines what I call here G3 of Q R W. Okay, so I'm kind of forgetting about G here, but as I said earlier, I'm just going to consider a nested scheme, and G will nested quivers, and G will just be an inclusion. Okay, so that is the new object we have defined. Again, it has very explicit descriptions in terms of generators in degree -2, -1, and 0. But I won't give it here. I tried just to make you feel what it is in the coming examples. So before that, I have a Lagrangian correspondence here. And since I have nothing here, it just means that this Calabi Yau cospan, excuse me. So this just means that the morphism here is Calabi Yau. And we know, thanks to Brav and Dijkhoff, that it induces on the perf Lagrangian structure. And it's the fact that we prove that it actually matches the usual Lagrangian structure on this morphism. All right, so another example that will again probably remind you of Tudor's talk earlier. I consider the same nested schemes as nested quivers, sorry, as earlier. So the one loop quiver in the 3 loops quiver, except that I add framing. So you can guess I'm going to talk about the Hilbert scheme very soon. I keep this large quiver endowed with my same potential as before. And what I want to do is really transfer this results we got in the derived setting to the non-derived setting and try to get some genuine Lagrangian subvarieties. So the first step for that is first to restrict ourselves to the open substack where we specify a dimension vector. So the one here is for the framing, okay? And we consider here the derived representation stack of our quiver, our small quiver R. All right, and the fact is that you can understand the Hilbert scheme of endpoints on the plane. So first we know that there's a nice quiver description here, roughly thanks to Nakajima. So we have a pair of commuting matrices that act cyclically on some vector V, right? So that's exactly the stability condition for this in this setting, which yields a free quotient by GLN acting on these 2 loops. Okay, so one can remark that this can be obtained considering the cotangent of this guy, considering its 0th truncation, that's what I mean by tau 0 here, and then taking stable representations. So that's how I kind of underive my Lagrangian structure at the arrival. But then I can actually deal with the critical, relative critical locus, taking some pullback over my cotangent and with my Hilbert scheme. Truncating again at in degree 0, I get from the results here. So we get a wider result involving any pair of nested quivers, but just give you here in this example. I get a new variety, okay, lambda n1 in my Hilbert scheme, which is again going to be Lagrangian. So I have this description that very much look like the one I had before taking any quotient or stable points, which is triple XYV here, where the matrix commuting with X is actually a commutator of guys commuting with X itself. Okay, so I can actually we can actually go a bit further. why? Because the issue is that we might want to get Lagrangian subvarieties that behave better than this one. And by that, I mean that there's no easy factorization structure that we can put on these Lagrangian subvarieties, which is a problem, for instance, if we're interested in putting some hop structures on cohomology groups of our Lagrangian subvarieties. So the idea here is what I call saturating our Lagrangian subvarieties in a way that I will explain shortly, with respect to the Hilbert-Shaw morphism of given by denoted by rho here, that maps a triple XYV on the joint spectrum of XY, which makes sense since these matrices commute. All right, so by saturation, I mean this. I'm gonna look at the image of my subvariety lambda n1, and then take the pre-image that I call Ln1. I have a different description, but easy to express here. This time, I get a subvariety described this way. X and Y commuting, it makes sense to require that on every generalized eigenspace of X, the trace of Y to be 0. It is, and we again get something Lagrangian. So again, this appears to be something new that we haven't found in the literature before. It actually has more irreducible components than the previous one. So in a way, some orbits are made larger, and this time the irreducible components will be indexed by unordered tuples of partitions, okay? Each of these partitions corresponding to the nilpotent type of X on each generalized eigenspace. So that seems pretty new. And it turns out that this saturation process gives a way better factorization property. So what I mean here is that if one considers two disjoint open subsets in C2, which is where we want the eigenvalues of xy to be, I can define Ln1 of u like this. So expressly require the eigenvalues being in U. And then what I vaguely say as up to some principal bundles, so which means that there's an incidence variety somewhere here with nice fibers. While the requiring the eigenvalues to be in U and V is pretty much the same as considering the product of these two Lagrangian subvarieties. So that's something pretty nice that's been kind of properties that have been used before. For instance, to define coproduct of geometric origin on some cohomological whole algebras associated to maybe at least the Hilbert scheme itself. So we could wonder if the same can be done on the cohomology groups of these Lagrangian subvarieties if we consider these in a family making n vary. This is also very natural to wonder if the irreducible components of such Lagrangian subvarieties appear in some characteristic cycles associated to modules over some Cherednik-like algebras, or more or less equivalently as singular supports of some sheaves over some moduli spaces of quiver representations, for instance. And I'm going to stop here. Thank you.
Okay, thank you. So are there any questions? Let me make sure people are able to, yes, people are able to unmute themselves. So you can just unmute yourself and ask by voice or raise your hand.
So in what generality is this, are you constructing these new Lagrangians? I was a little confused what the exact generality was supposed to be.
All right, so I said I got a Lagrangian structure on a Calabi Yau structure on this morphism here, this morphism. So the generality here would be to replace G by any morphism of dg categories here. So yeah, you don't have to restrict yourselves to the quiver case. If you do so, then I have a Lagrangian structure on something like that for any pair of nested quivers R into Q and any potential W.
And sorry, what's G in this theorem? Oh, G is the map from one quiver into the other quiver. Okay, I see.
Yeah, and in my examples, it's just the inclusion.
I see. Okay.
So it's,
is there any relation between the G and the W, or they're just independent there?
Here they're independent. Oh. So W comes from the W it's just related to Q.
Okay,
so don't have to restrict in any ways to R or whatever, as you can see in the examples. But it's a good question to wonder in which cases you get something actually interesting, and there's a lot that can be done when you consider a multiple loops quiver. I guess if you consider I don't know, W to be a cycle in some a fine quiver, you won't get, I'm not sure you will get new Lagrangian subvarieties. These will most of the time look like realistic ones. But yeah, for the full generality, maybe you should, I mean, Sarah talked about the full generality of the stuff. So that was way more down to earth. But I mean, the quiver case encodes a lot of stuff already. So yeah.
Yeah. May I ask a question about your last proposition, which is in purple on your last? Yeah. It looks like you like cotangent bundles very much, but there are some other possibilities to generalize Nakajima's story, which is really three-dimensional, and the geometry is like not like in Nakajima, like three-dimensional complex space and one coordinate plane, but let's assume that you have three of them. I mean, instead of Hilbert's scheme, or if you kind of replace your framing dimension to higher its moduli of instantons of fixed rank, now you have still symplectic manifold, yeah, which is a moduli space of Nekrasov spiked instantons. In that case, you have like three possibilities, even if you take the framing dimension 1 for each of the three. You have like three copies of Hilbert scheme, but they will interact in a non-trivial way, some kind of a fiber product over common intersections. I'm just wondering if you can construct a Lagrangian in the Nekrasov moduli space. It's complex symplectic. Nothing prevents from having a nice Lagrangian, but it's not a cotangent bundle.
Yeah, no, I understand. Yeah, this is a pretty recent work, and we're actually still looking for interesting applications. And yeah, we've looked into Nekrasov work recently because he was he's also been working on this Young Mills stuff. So I'm sure I'm sure it can be interesting, yes, because there's plenty of possibility with this kind of diagram. I mean, the thing is that here, when you take the perf of G2 of something, you get the cotangent of something. So if I stick with this G2 here, I will always end up with a Lagrangian subvariety of a cotangent of something. But as Sarah said the other day, I don't have to consider two Calabi Yau stuff here. I can put something else. So that's definitely a good idea to find a new construction from this. I'd love to look into it. Yeah.
Okay.
But I haven't yet.
Hi, I have a couple. I have a couple
yeah,
questions. Maybe they won't take so much time. So a couple of slides ago, before this one, you had this. I think one after this one. Yeah. So there you look at only the stable locus. Do you have a good description of what happens if you take the semi-stable locus of this strictly semi-stable part of the stack?
So all right. So when you consider the one vertex quiver, it's pretty difficult to find interesting stability conditions. So in this condition, I'm not sure it makes sense to consider semi-stability instead of stability. So you see, I said here that according to Nakajima's definition, this means stability. So there's no such thing as semi-stability in this context, I believe.
I thought you meant there was like a GIT stability thing.
Yeah. But again, so here there's just one vertex here. So a stability condition is just a number, theta.
Mm-hmm.
And yeah,
okay.
I don't think there's anything interesting you can say here.
Okay. Another question is about these new Lagrangians you found. Do you have some idea of what you're going to get by quantizing them?
No, not yet. So no, that's what I wanted briefly to say here. So that's one direction, is to understand what could be done that looked like, for instance, Kashiwara and Rouquier did about the, using the Calabi Yau spaces and stuff like that, and linked to Scherotzke algebras. But no, not yet. I try to see that if these Lagrangian were satisfying some criteria that should be satisfied in order to be characteristic cycles. It seems to work, but I still have no idea how they're related to this, or how they can be quantized. But that's a good question.
Okay, thank you.
I have another question. So at the very end, you mentioned that this sort of new saturated Lagrangian has factorization property. Does it mean that you can like construct a Lagrangian, say, in Hilbert scheme of K3, like for instance, sort of like use this factorization property to go from C2 to something else?
Yeah. Yeah, I don't know. But yeah, this C3 business seems to be very interesting. I have to look into it. So far, that's all I can say. That's a good justification for me to consider this process. But I haven't got time yet to go further. But that's definitely the idea. Yeah.
Okay, and another quick question. So, like, did you try to consider maybe, so like when you consider nested Hilbert schemes, usually they are not smooth unless you impose some conditions on support, of steps. And like, what if you consider like nested Hilbert schemes where like points live in one of your Lagrangians? Like, does it help you to get something smooth or not?
Yeah, I see what you mean. So usually it's nested Hilbert schemes are not smooth except if there's just one point difference in the support, right?
Yeah, and I think the point is that if you sort of like add only points like on A1 inside A2, then it's fine. So like, and this looks like just, you could replace this Lagrangian, but your Lagrangian or something.
So here there's a pretty nice description of what I get here. So you can see that you can, on one line you have the eigenvalues of X, and then or transversely you've got the eigenvalues of Y over each generalized eigenspace. That since the trace is null, 0 are kind of balanced around these eigenvalues of X. So this is a nice description, and it would be a good idea, yes, to wonder what happens if we consider nested Hilbert schemes with eigenvalues in these kinds of balanced subsets. That's a good idea. But I don't know if there's any chance to have more, to be less singular than in the usual case. I don't know.
Did you compute a generating series for the number of irreducible components, say in this case?
Yeah, so yeah, no, but it's I mean, yeah, I'm sure it's maybe I had looked a bit for that because it seems to me that it's something pretty natural. So I said that it was unordered tuples of partitions. So you see that you could kind of partitions of partitions. So I'm pretty sure there's a very explicit and easy way of writing a generating series. It's like, it's the same indexation as the generalized reduction of an endomorphism, right? A partition for the spectrum, and then for each eigenvalue, a partition for the nilpotent part. You see what I mean?
Yes.
So I remember having looked if there was a name for that, or yeah.
So it should be some exponential of something, statistic exponential of something.
Yeah, maybe a
something
double
positive.
Maybe a double exponential.
Okay, thanks.
So I just wanted to mention that the next talk will be Pavel Safronov in 6 minutes. People can keep asking questions if they have more.
Yeah, in particular, I think that Alex Takeda has his hand raised, which maybe means that he has a question.
I already asked the question. Thank you. Yeah.
Actually, maybe another good question. So could you like give a quick example why this lambda and L are different? Sort of like for n equals to 2, are they already different? Or I mean...
Yeah, it's kind of simple to see how this one behaves better. So imagine you want X to be say the regular nilpotent guy. Well, then you see that here any Y will be 0. Okay, commuting with the commutators of two guys commuting with J is 0. Whereas here, I just asked Y to have a null trace. And to commute with it, of course, but yeah. So that's bigger. And you can feel that it's easier to manipulate. So, and you see that you see that you get different dimension here, clearly. And this is why you've got more irreducible components in this case. In the previous case, looking at X, this nilpotent guy the orbit doesn't produce something large enough to be in a reducible component. So it's in the closure of some larger orbit. Whereas here, you get for each reduction type of X, you get an irreducible component.